Okay, let's I guess get started. I trust people can hear me out in TV land. Um, the first, let's start off with any questions about anything. Yes.
In homework three, for second probability cost, do people shop more during holidays or before the holidays? So does it mean like a day before the holiday, a week, or like on the holiday or on a normal day?
Okay, so the question is about on homework three. There's a question about do people shop and the
Before the holidays. That is the
do they shop on the holidays or before the holidays? Okay. Um, As far as I am concerned, you should answer what question seems like it's the interesting one to you there. Okay. If one of if the TA would like to give me a resistance for standardization and tell me what they would like it to mean, I'd listen.
I think we're more asking something like analyze how people's behavior change during the holidays, like maybe the whole of December or Christmas, and how it like slowly drops on the Christmas, something like that, and analyze that in the regular week pattern of
Okay, so you're interested in the period, not just the act by holidays. You don't mean the actual day. You mean maybe a lead up period.
yeah. So the question is basis on and before the holidays.
On and before the holiday. So you could imagine a world where everybody knows they're going to shop on the holiday, and therefore they don't buy anything for the week before. You could imagine a world where everyone says, if I'm going to have a holiday, then I darn well am not going to spend it in a store, and they'll do more shopping beforehand. And there's a question then of you know trying to understand what their behavior is. Okay, so give it a, try to get a sense of it. Any other questions about homework three, which should be starting to rear its head in your mind a little bit? Okay, any questions? Actually, if everything goes according to plan today, I'll talk about the last thing that you will need for homework three. So it is time for you guys to think about that. Any questions about projects? There is at least one project where we have made additions to the file to point people to a data set or something like that. So it's okay to go back and look at the project statements, but you guys should be thinking about that. And if you want to talk to me about that, that's a perfectly reasonable thing to do. Okay, any questions about projects or homeworks or anything like that? Okay, if that's true, what I'd like to talk about today is the last couple of classes we were talking about statistical distributions. Um, Today I'd like to talk about the question of statistical significance, which kind of gets at the heart of when you see something, is it kind of just chance? Okay, a great thing to, again, people are going to be asked, ideally, you're going to be analyzing data sets, you're going to be making things that seem like discoveries to you. And sometimes it's because the data just kind of, you got lucky, you're seeing a false view. Sometimes you really make a discovery that means something. How do you tell if something is a statistically robust result versus an artifact, versus a, um, something that is not as amazing as you think it is. Actually, I have a good example of that came up, this over the last year in work that I'm doing. I do work with neuroscientists, and we had this theory of, something that should happen. Obviously, it was about we were studying, things like Alzheimer's disease, which happens as you get older. And we would like to see, would expect that, people who are going to get Alzheimer's, their mental acuity is going to, they're going to start having problems at a certain age. There's going to be a transition from when they didn't have problems to when they did have problems. And, we had a possible cause for this that we had observed in data. And we saw amazingly that people who had this cause, when you looked at our curve, looked like they got mental degeneracy 5 years earlier than the rest of the population. And if so, wow, this is great. We found a real cause of Alzheimer's. And it looked like a fabulous plot. I mean, this was as beautiful a plot as I'd ever seen. But then we asked ourselves, well, is this, and it said exactly what we wanted it to say. And then, we looked into, I said, wait a second, is this really statistically significant? And we ran 20,000 other causes, okay, that could have been, causes of Alzheimer's. And roughly, and a non-trivial fraction of them showed the same thing in ways that were no greater than chance, okay? And so, in fact, our dream finding was nothing more than a spurious correlation, okay? And, our dreams of future grant proposals and things like that shattered, okay? And that's kind of, I guess, you can call that, I don't know if you call that a happy ending or not, but the question is, can you tell when something is real versus a spurious observation? Now, computer scientists usually don't lose very much sleep about spurious observations, usually because their study of data isn't so important. Okay, that might be a little bit of an overstatement. But computer scientists are usually very excited to tease data for all it's worth, and they'll do something, and if they see something, they'll say, wow. Statisticians as a group tend to be people who are concerned with, have a tradition of being very conservative, of worrying about whether things are right, having formal notions of whether things are right. Now, I think that makes it very unpleasant in general to talk to statisticians, okay? But there is a certain value here that I do, it's important for us to have a certain sensibility about that. It's easy to use data, it's easy to find patterns, it's easy to make a nice graph. The question of, is that pattern significant? And that's really kind of what we're trying to get back. What are the chances? What does it mean? If you have a strong enough correlation on a large enough data set, then what you're seeing is probably real. But what is strong enough, and what is large enough? And that's kind of what statistical significance testing is supposed to try to get at. Any questions here? And again, we saw this very much actually in the COVID epidemic. If you say sort of what is the canonical thing a computer science student goes off and does? You would say, you go work for Facebook or Google or something like that. What is the canonical thing that a statistician does? They go off and work on studying, whether or not a drug should be approved. Okay? That, you end up with problems like this. Suppose you have a drug for curing that you think is a cure for some kind of a relatively rare disease. Okay? Suppose drug A cured 19 out of 34 patients. Drug B cured 14 out of 21 of these patients, 21 patients. Is drug B better than drug A? Okay, I don't know if people have a feeling here. On one level, as computer scientists who are good at taking the mean, okay, you would say, hey, 2 out of 3 patients got cured by drug B, okay? Whereas, only about half the patients got cured by drug A. I'm taking drug B, okay? Now, the question is this the result of drug B being better, or is it something that would happen if you just kind of tossed random coins? Suppose both drugs cured half the people. What's the odds that drug B could have cured 2 out of 3 in a small enough sample? The question of whether a new drug is a real improvement on an old drug, okay, is the kind of thing that medical the FDA approval kind of rests on. Now, we as computer scientists will say, fine, how do you solve this problem? We would say, get 1,000,000 patients. Why not give each of them the two drugs, give half of them the drugs, and after 1,000,000 people, you'd know. The trouble is that most diseases are rare. It's very expensive to run these trials. You can't, sacrifice 1,000,000 people on this thing. Okay? And this is why, kind of the field of medical statistics and significance testing is really important. Any questions? I remember being surprised when during the COVID epidemic, there was this, at one point in the epidemic, there was this drug that was relatively early, this drug that was being touted by, President Trump and among other people that had come out. There had been a little study that showed that it looked like it worked. President Trump got right behind it and said, this is great, let's just take it. And the scientific establishment said, well, I don't know, there's not enough evidence. We don't really think so. And when they ran more and more tests on it, it seemed that the drug was ineffective. Okay, and it's no longer considered a viable candidate for anything. So there is a world here where you have to be careful, and that's statistical significance testing. Any questions? Okay. Now, basically, again, you're often you're going to be building a classifier, okay, and you're going to want to know whether one classifier is better than the other one. Again, you guys are going to, this is going to happen kind of on your homework 3, but a realistic thing is you have some data, you train some models, one of them is going to give you a better test score, probably by a little over the previous one. Which model should you use? Okay? If you just view the test score as being the God's gift to the world, then you would pick the second, the one that did better. But it's sometimes important to tell, are they really doing differently? Okay? And that's kind of where statistical significance testing will come in. Okay. Probably the simplest, most important statistical test, most popular statistical test to do is something called a t-test. And a t-test is going to ask whether the population, if you have two distributions, whether the population, the means of the two different distributions are different. Okay? So let's imagine a world where we pick at random 20 men from this class, and we go at random and we pick 20 women from the class, and we give each of them an IQ test. Okay? And that centers, the average is, normal people in the population is 100. I think you guys probably on average are a little bit above that, because you're in grad school. If we do this for the men and the women, what is going to happen? If I take 20 men, give them IQ tests, 20 women, give them IQ tests, is the average of each group going to be the same? No. Why not? Think there's something different between men and women?
Generally, women of the same age are considered more mature than men.
Okay, you're saying there is something different. Okay, you're saying, I think you're going to go there and say the women are smarter. Okay, maybe. Okay. Okay, so you're saying 20 is a small number. What I can almost certainly guarantee you is that if you have 20 men take an IQ test and 20 women take that IQ test and you average it, the means are going to be different. It would shock me if they got exactly the same score. You sum up the scores of the 20 men and the 20 women, and they came out the same. Okay? Now the question really is going to be, so there's going to be an observed difference, okay? So the answer is one group smarter on average? I'm going to say almost certainly yes, by the just the results of random sampling. Now the question is that difference going to be a meaningful difference? I mean, if the difference was the women averaged 130 and the men averaged 70, then I think, probably, you see a difference, right? But how do you know if there is a difference between the mean of the two populations? Okay? It should be clear that the mean is again, we said the mean and the standard deviation represent a distribution fairly well. It should be clear that it's easier to tell if men and women have different IQ if there is a bigger gap. On the top row here, we have two distributions. They have the same standard deviation, but different means. Does everybody see that on this mean, this figure on the right, the means are fairly far apart? Where is the mean? The mean here is at -2 and 2. Okay? There is some overlap of the distribution, but relatively little, right? It should be clear that if you're randomly sampling from the red distribution and the blue distribution, the farther apart the means are, the easier it is to tell them apart. It should also be clear that if the means are about the same, okay, then it's very, very hard to tell apart. The other thing is that the variance affects whether or not it's easy or hard to tell the two apart. Here we have two distributions, okay, where two distributions where the means are fixed, but the variance is decreasing as we go along this way. Does everybody see that in this distribution, where the variance is relatively small, there is less overlap between the distributions? There's less noise in some sense. If you sample from it, okay, you're more likely to see a difference in the distribution here than there is one here, okay? In an ideal world, if we had two distributions, Vump and Vump, even if they were very, very close, if the sample variance was very, very small, it would take only one or two samples to tell a population apart, right? Okay. So what is the idea of a t-test? Okay? The t-test has the property that we know three things basically. If you have two samples, okay, two samples with distributions where you sampled from, and you can observe in your sample the sample mean and the sample standard deviation. What do we know? If two means will differ if the mean is relatively large, the mean difference is relatively large, the standard deviation is relatively small, and you have sampled a large number of samples. Clearly it becomes easier to tell, let's say height on men and women, where I think we all agree that there is a difference. Okay? If you randomly sample, the more men and women you sample, the more confident you'll be in your conclusion. The bigger the difference is, the more confident you'll be in the conclusion. The smaller the standard deviation of each distribution, the more confident will be able to tell them apart. Okay. We are having a fire drill here. So I am going to have to, actually, here's something I'm going to do, which is probably going to be a disaster. Actually, I think we're going to leave and, let's say I'm not going to try to teach outside. Let's go outside because we're going to get in trouble if we don't. and I'll see you guys. Everybody run outside before you get burned up. And I'll be back here in a minute, hopefully in a few minutes, to resume teaching. Okay, thank you. Sorry about this. Okay, everybody get up. Hi there, guys. We're coming back. Okay. Okay. Let's get everybody settled in here. I'm sorry about that. Okay. Let's see. I think we're all settled in now. Okay. So what are we doing? We were back on the t-test. And what is the t-test? We're going to compute a statistic, okay, called the t-statistic, and there's different flavors of it, depending on what test you're going to do. But basically, t is for the Welch's t-test. It's the observed mean of the first distribution minus the observed mean of the second distribution. Okay, divided by the square root of the variance of the first. Remember, square of the S is the standard deviation. The square of it is the variance. So it's the variance of S1, okay, over the number of samples of S1, plus the square root, plus the square of the variance of the second distribution, divided by the number of samples. Now, what does that mean? Notice that if t is, if the distributions are the same, okay, we would expect that, let's say we want to make them different. It should be clear that taking the difference here, the bigger the difference between the means, the bigger the absolute difference of the t statistic. Okay? Sorry, let me just do this for a second. Oh. Hold on, sorry. Sorry, I'm having trouble here for a second. Okay, good. So it should be clear that the bigger the difference between the means, the more positive or negative the t statistic is. It should be clear that as the variance goes up, what happens to the t statistics? Let's look at it this way. As the variance gets higher and higher, what happens? The t statistic decreases towards 0, right? Because basically, the bigger the variance, we're dividing by something bigger. What about the bigger so the more variance, the closer it gets to 0. The less variance, the higher, the further away from 0 it gets. Everybody can you see that? And what about the counts? As the counts get bigger, what happens here to the t statistic? Okay, I have a hard time telling this thing. But what happens if I multiply everything by like square root n by square root n? Okay. Okay, it should be clear that that's going to cancel the bottom, but it's going to be up top. The larger n is, the larger the t statistic is going to be, right? The smaller the variance is, the larger the extreme the t statistic is. The bigger the means distribution difference is, the larger the t-statistic will be. Okay, the bigger n is, the bigger the t-statistic is going to be. So this statistic does kind of what we want, okay, on all the factors that we have identified as being relevant to, just telling how far apart the distributions are. This t-statistic will have a higher absolute value the more likely it is that the distributions are different, okay? Or the less likely we have to believe that they are the same. That's probably a better way to put it, okay? Any questions? So what is then what do we do with that t-statistic? You then go to a table. In the old days, it was a table in a book. It's probably an algorithm now that you, some calculator on the web, you plug it into. But given the t number and given the t number, it will then look it up and tell you whether there is a meaningful difference or not. Okay? To be precise, what you do is when you're using one of these tests, you specify a confidence level, okay, a p-value, such that you want to know, is this value of t-statistic likely to have occurred by chance with a probability less than something? So people usually talk about a statistical significance level at the 0.05 level or the 0.001 level. You specify in advance what is your threshold of the chance that you're willing to say that that I'm willing to accept the possibility that this observation occurred by chance with a probability less than or equal to p. And then, given this significance level that you specify, the amount of confidence you demand, and given the t-statistic, you go to the right table and you look it up, and it will tell you, is it significant or is it not significant? Any questions? Okay. That is basically how the t-test works. Okay, and I believe you are destined to do one on your homework thread. Any questions?
From the table we get a value.
Yes.
So from that value, how can we judge that it is significant?
Okay, so what you're going to do is from the t-test, okay, typically what is happening is you get a value of t. You have a level of security that you demand. Okay, that's a p-value. Okay, what's the possibility that this, I'm willing to accept the possibility that this happened by chance, right? Is it possible that if I sample, people in the world, I happen to get, by chance, the 100 tallest women and the 100 shortest men? Certainly there is some chance of that, right? You're never going to rule out the possibility that your sample was incredibly unlucky. But given given the level of luck that you're willing to swear off, okay? Look it up in the table. You give it the t-statistic, and it will then tell you whether it passes the test or fails the test. Okay? That's basically what it does. Okay? The table is basically going to tell you for what values of t do you have to be above to pass the test. What?
Above the p-value.
No. Right. Given you specify the p-value in advance, I demand to be sure that I want to know what's the chance I see this difference with a probability less than 0.05, 1 in 20. Okay? Then you look up in the table, and the table will tell you what value of t did you need, okay, to achieve in order to get that guarantee. Okay, if you exceeded by more, you probably would have exceeded it at a better guarantee, but that's not the way that the table works. You specify how much confidence do you want at the beginning. Okay, you compute the t-value, you look in the table, and basically it'll tell you whether you pass or don't pass. Any questions about that? Okay, so this is the way I find when I hear this makes a statistical test sound like voodoo. You're consulting this magic table to tell you how much of a t-statistic was interesting. Okay, and where does that t-value come from? Well, this is why God invented statisticians, to work out this kind of thing. But in some sense, you can think about it. Statistics is based on sampling. The presumption is that you sampled these people at random, okay? And you can start to say, well, if the populations really are different, how weird is it that I drew a sample from the first population that gave me the statistics so close to the sample of the other population? And, there are ideas like Bayes' theorem in there. There's, understanding, some of the sampling. I'm not going to go through this thing, but we should recognize that there are some ideas underneath here that are necessary to build up a table like that. Any questions? Okay, so that is a t-test. There's another statistical test that I happen to use. I happen to personally find more satisfying than a t-test. It's something called the Kolmogorov-Smirnov test. Okay, the KS test, I usually call it. And what this is doing is it's not just looking at the mean and standard deviation of your two samples. Again, what's the basic problem? I've got men I sample from, I've got women I sample from, be it their height, their IQ, whatever you want, okay? And I want to know whether these two samples are from the same population or different populations. Usually, if they're in different populations, that's the thing that's kind of interesting. You want to, you might want to know, let's say, you take Skinner's data science class, you take other people take somebody else's data science class, you give everybody a test at the end. Do the people in one class do better than the other class, or are they really the same population? So what's the KS test going to do? The t-test, remember, looked only at the mean and the standard deviation in the number of samples, relying on the fact that the mean and the standard deviation and the number of samples tells you a lot about the shape of the distribution. The KS test instead builds the cumulative distribution function of both sets of samples. So let's think about when we take the number of samples, our y-axis is going to be what fraction of the samples have we seen so far. The x value is a threshold of less than or equal to x. The cumulative distribution is going to mean we're going to go move from left to right, okay? And every time we see another sample, we're assuming we're sampling values of x, okay? We tick up the cumulative distribution at some point. We know that for a small enough value of x, we are less than all the samples. For a large enough value of x, we have seen all the samples. Does everybody kind of agree with that? So the cumulative distribution is going to be a curve that only goes between 0 and 1, and only goes, and ticks up whenever we have a sample of that size. How far does it tick up? It takes up 1/n of the way for every sample we have seen. So now let's take a look at a world where we've got two different samples. There's a blue sample and a red sample here. Okay? Both of them will define a cumulative distribution. Okay? Again, the number of samples in each distribution might be quite different. Okay? If the red distribution had fewer points, the steps up are going to increase. But in both cases, they're going from 0 to 1. Now, what is the KS test going to do? Once you've plotted these distributions, you're going to find what is the value of x where there is the biggest cumulative difference between the red sample and the blue sample, right? If they were sampled from the same distribution, you would like to think that there's never going to be that big a difference between them. If they were sampled from different distributions, somewhere there's going to be a bulge, okay? And the two distributions are going to differ, okay? The KS test says, find me the biggest difference that you can, okay? And that's going to be my statistic D, okay? And it basically is going to ask, sorry about this, is the difference, the size of that biggest difference, greater than something here that is, if the two sample sizes were the same, about 1 over square root n, times some confidence number that some coefficient you're looking up in a table. You specify what is the significance level you need. I want to know, are these two samples the same to a confidence that, again, alpha might be equal to 0.005, alpha might be 0.001. This says basically that the chances of it happening are, of seeing a difference this far big, if the distributions are the same, is less than 1 in 1,000. Okay? This would say, what's the chance that the chances of seeing a difference here, okay, as big as I'm seeing, is, if they were the same distribution, is less than 1 in 20. You specify alpha, you look up this constant in a table, and if the difference is more than a constant, that constant times 1 over basically the square root n, the distributions differ. Otherwise, you have to assume that they're drawn from the same distribution. Any questions? Now, why do I like this thing better than a t-test? It's still looking something up from a table, which sounds weird to me. But I recognize a few things that I understand. One is this 1 over square root n. Have we seen 1 over square root n any place in this class before? That was kind of related to the standard deviation of tossing coins. Okay, if you use a geometric distribution, right? That's kind of what we would expect if you're tossing heads. If you're tossing, let's say this was doing heads and tails. Okay, you have two people. Tanzir is tossing a coin, okay, and he's coming up with heads and tails. And I'm tossing a coin, and I'm coming up with heads and tails. How do we know whether one of us is using a loaded coin, okay, a biased coin, or are we using the same coin, right? Well, we would look at what's the rate at which we're getting heads along the way, right? And it's perfectly reasonable for us to differ in the number of heads by up to something like square root n. And then that we're probably still using this, both using fair coins, right? Or equally fixed coins, okay? But if the deviation is too many times square root n, then we get, it's fishy, okay? And so this I have at least a little intuition about. That's one reason why I like the KS test. Another thing I like about the KS test is it uses the whole distribution. So if there are weird places in the sample, let's say you had a mix of people, a small number of people whose IQ were measured in some other unit, okay? An artifact like that would tease out as a bump kind of maybe over here, okay? The third reason why I like the KS test is that I get a picture, okay? Instead of just having you, consulting some table and it telling me, yes, there is a difference or no, there is a difference. I get a picture and I get to see where the problem is. And I can decide, yeah, does that look right to me or does that not look right to me? So these are reasons I happen to like the KS test. Any questions about that? So here is an example of the KS test where I wanted to tell whether or not a set of numbers were normal. Okay, we remember we've been talking about the normal distribution. You have this idea that the normal distribution got a mean and a standard deviation. Suppose we drew a lot of samples from the normal distribution. How do we know whether, let's say you want to know if height is normally distributed, okay? We could imagine measuring the height of 20 people in this class, 100 people in this class. There is going to be a mean, there is going to be a standard deviation, right? There's going to be a bell shape to this thing. Is this really being drawn from a normal distribution or not? Okay? Again, I told you no, but that's not really the gospel here, right? What you could do is the following. You could plot the cumulative distribution of your sample. Here the red is the cumulative distribution of the sample. What do I know should happen on the cumulative distribution? At the mean, if we think, what should the cumulative distribution of the normal distribution look like? Okay? We agree it should go up. How should it go up? Okay? Should it go up like this? Or should it, because there is more concentration around the middle, should it start going up slowly, then ramp up and come over? I claim it should look a little more like the red line here than the purple line. Does everybody agree with that? Okay. What is this? If you look at this red sample, of course, it's not quite like a logit function. It's not an exponential decrease in some way. What did I do? On this particular case, this is measuring the red was data that was drawn from a something that was normal, supposed to be normally distributed. Let's say it's height. Okay? Not sure that it was, but let's say it was. The blue here were samples I drew from a uniform distribution from over the same range of numbers. Does everybody agree that the shape of these two, there is a place where there is a big gap between, okay, the normal values and the red values and the blue values? This is a big enough gap that it's clearly going to be unlikely that if I knew that I had sampled the blue from a uniform distribution and the red were the heights, this is enough to rule out the idea that heights were uniform. How would I tell whether or not heights were normally distributed? Well, what I would do is, suppose I drew a random sample. I knew what the mean of my observed distribution was. I knew what my standard deviation of it was. I calculated that from the sample. Now I go to a procedure where I sample from a normal distribution of that mean and that height, that mean and that standard deviation. It should be clear that computationally I can get a sample like that. And now what do I have? The red corresponds to the heights. The blue corresponds to a sample from the theoretical normal distribution. If the heights were normally distributed, there shouldn't be a big gap between the two. Does that kind of make sense? It should be clear that the normal distribution is a theoretical construct. I can make samples from it at random. Okay? In fact, I'll show you how to do that in a few minutes. But what can I do? With the KS test, I can do a sample from the normal. I can look now, how does the cumulative distribution of my theoretical sample compare to the heights that you observe in your, real sample? Okay? If the deviation is small enough, then darn it, the thing is normal. Any questions? Okay, and in this case, the deviation was small enough. In this case, the deviation was too large. Any questions? Any questions how a KS test works? So I like KS test. Okay, any questions? Now, when it comes to statistical significance testing, again, what does it mean when you have a significance level? When I say I have validated my hypothesis to a significance level of 0.05, that means that there is a 1 in 20 chance that we saw that if the two distributions were the same, okay, you would see this big a difference. Okay, that's really what it comes down to. Now, one thing that's funny is if you run statistical tests in isolation, you sometimes end up with weird things. What is this graph up top? This graph here is a graph I took from somebody, which plots the total revenue generated at video arcades by a year. This looks like what years? This is 2000 and maybe that's 2000 to 2009. Okay? The red line plots the amount of revenue generated by a video arcade. The black line says how many PhDs were granted in computer science that year. What can you observe about those two plots? Okay, is it clear that there is a very, very strong correlation between them? I know you may not be able to see it that well, but certainly if you're here, if you look at this thing, it turns out there is an incredible correlation here between, in the observed 10-year period, between arcade revenue and CS PhDs. Now, what are the chances that you would get a correlation that's strong on only, these 10 points? And it turns out to be extremely low, certainly less than 1 in 20. Okay? Does that mean that computer science PhDs correlates with video games activity? Could be people watch video games and they suddenly decide to get a CS PhD. Could be people try to get CS PhDs and they go crazy and start playing video games. Or it could be that it's a spurious correlation. Which do we believe that it is? Okay, does anybody have a belief? Okay. Who here votes spurious correlation? Yes, okay. Now, why is it that there is such a strong correlation, but it doesn't mean anything? The reason is because of how this figure came about. The guy who wrote this, there was a guy who wrote this book, and whose name I am unfortunately remembering, where he analyzed a bunch of time series, compared every one against every other one, and found the best spurious correlations he could find. It was a funny book, okay? Now, what was the point? If a significance value of 0.05 means that there's a 1 in 20 chance this could happen by chance, if you run 1,000,000 of these such tests, what's the likelihood that how many of them are going to be significant at the level of 1 in 20? Well, 1,000,000 divided by 20 is what, 50,000? Okay. What it means is that if you run lots and lots and lots of statistical tests, some of them are going to score above chance just because you've seen it so many times, you've tried so many things. Does everybody agree? If you flip coins often enough, you're going to get 10 heads in a row, right? Does that mean you're great at flipping heads? Okay. No, it means that you happen to have gotten lucky at this point. Okay. So what is the big picture? The big picture is that if you're doing a fishing expedition where you're going to compare lots of things against lots of other things, some of them are going to correlate pretty well by chance, right? You need to decide whether you really like trust one of these things. You've got to do an extra statistical correction based on the number of hypotheses you tried. Okay? If you test n hypotheses, it turns out that your significance of interest, let's say you want to know, what was this test? Was this particular comparison between computer science PhDs and video game things? If this was your one theory you came into the room with and said, I'm going to try it, I think video games drive people to computer PhDs, then you ran that test. If you did a test at a significance level of 0.05, if the score came in high enough, there was only a 1 in 20 chance this happened by chance. On the other hand, if you tried n different hypotheses, computer scientists against, against video games, stock market against butter production in Bangladesh, a lot of these other different hypotheses, then the relevant test for whether you trust it is not whether it comes in at the 0.05 test, but whether it comes in at a stronger condition. And the Bonferroni correction is a way of strengthening the level that you have to achieve before you kind of believe a result, where you do a lot of these tests. Okay? So in the Bonferroni correction, suppose you're going to test n different hypotheses, and you want to know which ones, do you trust to the level of 1 in 20 by chance. What you really need to do is to test not whether they reach the 1 in 20 level, but whether they reach the 1 in 20 over n level. The more hypotheses you test, the higher a level of standard you need to do to any of them before you kind of believe it. Any questions or comments about that? Yeah.
Suppose if we take two features from a data set,
Yeah.
then we do a case test or any test on that, and suppose we get that it is statistical significant. So should we believe it blindly or should we do something else?
Okay, so the question is, if you check two things and you see it and you do a KS test and it says it's significant, should you believe it blindly? First of all, nothing in life should you believe blindly. Okay? There could be other reasons for it. Okay? That are would have made it obvious that they were really should be the same thing. If somebody had made a mistake and copied the data twice, the fact that you saw that they looked the same, the statistics mean nothing, right? But I would say that you shouldn't be worrying about sampling problems when when you pass, if you do a single hypothesis test on a single thing, okay? If you're doing a fishing expedition where you're trying all variables against all variables, and you want to know whether any of them have a significant dependency on each other, well, now you're in the world of the Bonferroni correction, okay? And you need a stronger evidence for the one that survives than just 1 in 20 chance or a 1 in 1,000 chance, right? That's the big point here. Any questions about that? Now, again, you see this this kind of issue come up in in medical testing. They told you that they run these drug tests, and these when you run a drug trial, this is a very, very expensive thing, and whether or not whether or not if the drug is approved, they can sell it and they make billions. If the drug is not approved by the FDA, it's worth nothing. And so these statistical tests as to whether a drug trial passed or did not pass is a big money decision. So sometimes they will say, like, actually what happened in a recent drug trial. Okay? They tried it on a certain number of patients, okay? And on average, it didn't do better than chance. But then they looked at it and they said, wait a second. Among the people we really gave a lot of this drug to, gave them a really high dose, these people their mental degradation grew more slowly than the other people. So that's a sign that in this population, the drug worked. Okay? Approve our drug. Now notice that that's a kind of a fishing expedition. They had originally done the test, does the drug work for everybody? And now they're considering just a second observation after they had seen the data. And if they're going to see a result like that, now they're in the world where they've tried a second hypothesis, okay? And they need to have a stronger level of acceptance, okay? It's like a Bonferroni world, okay? Any questions about that? Okay? So a common thing, like I said, I'm just going to say this one last time because this is kind of an important idea. If you are in a world where you're going to try a lot of things, a lot of pairs of things, and to see whether it's meaningful, the more experiments you try, you have to rise to a higher level of significance before you believe the result of something that looks really good. Okay? And that is kind of what we do mean by the Bonferroni correction. Any questions about that? One way or another. Okay, so what does it mean when there is significance? Okay? Significance is a measure of whether the differences you observe between the two things was likely to have happened, is likely explainable by chance, likely explainable by sampling. Okay? If you have a large enough number of samples, okay, you will find that very, very small differences between means will be statistically significant, right? If Tanzier's coin was fixed so that came out heads 51% of the time, okay? If I had and mine came out 50% of the time. If we had a large enough number of samples, it would be eventually clear that Tanzier's coin is not the same as my coin. Does everybody agree with that? He's getting too many heads for me to really trust him. Now, is the difference between a coin that came up 51% heads and 50% heads, okay, a big difference? Okay, he went to the trouble of fixing the coin to get it 51% heads. Okay, is it a big difference or not? Okay, if I was going to decide to bet my life on a coin toss, I wouldn't want to use his head. I would rather use his coin and bet heads, right? If I was trying to decide where we should go to lunch with, I'd probably trust his coin. Notice that there is a difference between the confidence that we are that there is a difference between the distributions and the importance or magnitude of this difference. There is a statistical notion of effect size, which is how big a difference is there really, versus significance, which is, yeah, there is a difference. Does everybody kind of get the idea what the difference between significance and effect size? Okay. Computer scientists who are usually able to get millions and millions of samples can often show a very, very small effect as being significant. That's good, but it may not be meaningful. So how do we measure the effect size? Okay. Typically, people might say, does one thing correlate with another thing? If one thing correlates with another, that means that feature X can be used to predict Y. People say that kind of small effects, a correlation of 0.2 typically is a small effect. It has you can use that feature for making some kind of a prediction, but it doesn't tell you that much. What percentage of the variance, what fraction of the variance does a 0.2 correlation account for? Remember we said something about r squared, it goes down as something like r squared. So that would be an argument that a 0.2 correlation would explain about 4% of the difference between one thing and another. Okay? Is there a difference? Yes. Would I bet my life on that kind of difference? Probably not. A correlation of 0.5, 0.8, that would explain 64% of the variance, right? So it makes a difference. Another question is, if you have two distributions, is there a significant, does one really tell you what the other? If they overlap by 85% of the area, then people say that's a large effect, okay? If you overlap by half the area, okay? This does not tell you that much about that, okay? So understand that there's a difference between significance and effect size. Any questions? Okay. What I'd like to now talk about is another way of measuring significance of an observation. How unusual is something? Instead of doing a classical statistics test, okay? We saw things like t-test, we saw things like the KS test. These are good ways of telling whether two samples are the same or different. But on the other hand, they require some brains in order to do. You have to understand a little bit about the statistics, the statistic test you're using. There are many different flavors of these kind of t-tests. If you go do a t-test, someone's going to ask you, are you doing a one-sided test or a two-sided test? Okay? Are you measuring, is it unusual relative to the mean, or is it unusual how big it is? There's lots of different subtleties there. Okay? There is another idea on how you can measure whether an observation is real or not that you get. That is, has the property that it involves computation, so people like us trust it, okay? And that if you think through it, You don't have to rely on magic tables and things like that. Okay, and it's called a permutation test. So what is the idea? Let's say you want to believe that you want to get confidence, are men taller than women? Okay? I think we believe that on average that's true. How would you get confidence on something like that? Okay? Well, one way to do it is if we compare what happens where we have a bunch of men and women and we have their heights. Okay? One thing that we could do is compare the average height of the men versus the average height of the women. That'll tell me we see a difference. How likely is it that that big a difference occurred by chance? One possibility is to now scramble the heights of the men and the women. For every height, flip a coin to decide if it's a man or a woman. Okay? And then compare the difference observed between the men, the fake men and the fake women. Okay? And see how big a difference it was. If the real observed difference was bigger than this random fake thing, we believe it more strongly. If we do a lot of random trials, and we're consistently the case that the difference between the fake men and the fake women is less than that we observed, then we respect the observed differences more. Okay? This is the idea of a permutation test. Okay, what we're going to do is we're going to take your data, we're going to build a random shuffle of it. Okay? We're then going to come up with a statistic that's going to measure what we think the difference is. Okay, how skewed the data set is. And then compare the skew in the real data set against the fake data set. Okay? And based on the statistic, okay, and where it ranks compared to the random samples, we will come to believe it or not believe it. So here is an example, okay? Here is a data set where we have a certain number of women and a certain number of men, okay? And we have heights. This is the height of the women. This is the height. The length of this bar is the height. If we look at this thing, we see some men who appear to be taller than any woman. Okay? That's what I'm interpreting that as being. But there are some women who are taller than an awful lot of men, right? It's not a clear-cut difference between the two of them. How can we decide how real the difference is between men and women? Well, what if we now take these heights and randomly permute them among the men and women? Okay? Here was the real data. Here was the permutation. Okay, hold on. Here is a random permutation of the heights. Now, if we take this data and sort it, just so it's easier to view, does everybody see that in this case, the fake women and the fake men both have relatively tall people, right? If we're going to tell the difference, tell how significant the difference is between men and women in height, we need a statistic that will measure what the difference is, okay? What would be a statistic to measure the difference between the male population and female population in height based on a sample? Can anyone come up with a statistic that would take data like this and that would get at the idea of whether that there's a height difference? Okay? If you wanted to measure the height difference in this sample here, how would you do it? Yeah.
The mean
You would what?
or taking a mean.
One thing you could do is to take the mean value for the women and the mean value for the men, okay, and compute the difference between them, right? The difference between the mean, delta mu sub men, mu sub men minus mu sub women, right? And we would believe that when we saw this data, there would be a difference in height, right? That we would see then. Now, if we take one of these samples, okay, do you see that we permuted the data? Now, there's fake men and fake women. We could compute the same statistic. Give me the height of the average height of the fake women, height of the fake men, minus the height of the fake women. Okay? And if we do that, we kind of expect that if the difference between men and women's height is real, that the real difference is going to be bigger than what we get from our random sample. And if we do a lot of random samples and compute the difference between fake men and fake women height, we're going to get a distribution. If the observed data is far to the right of the random samples, then this is a measure that difference that we observed is real. Okay? So what are we going to do? We're going to have a statistic, like we said, the difference between the male mean minus the female mean. Okay? And we're going to have a real value. Maybe it was here, maybe it was here. And we're then going to do a bunch of permutations of the random data, random permutations of the height data, mapping them still to men or women in the same distribution as before. Okay? If, after we've done 1,000 random samples, if we get a situation like this, where the mean difference in the random samples was to the left of the observed data, it was very unusual to get a difference as big as we saw by random sampling. It wasn't that we were unlucky and that we happened to get sample tall women and short men. It was that there's probably a difference between here. Okay? Whereas, if the observed statistic that we wanted was here, and when we come up with random samples, our observed statistic is within the body of that distribution, the difference we observed in the real population probably wasn't that profound. Okay? That it's what you would just see based on, on the data that you would expect it to be a sampling thing. Any questions about that? I don't feel I did a clear job explaining this, so I'm happy for some questions. Okay? Any questions? In general, what do we have? After you've taken a random sample of these things, if you then stick the real value here, if this was the real value, what is the likelihood, how unusual was that real value? Well, if we took the sum of the elements that were greater in the random sample than the real value, the fraction of these that were bigger than the observed sample, that is the confidence level that this was something that happened by chance. Suppose we did 1,000 random samples, okay, and 50 of them happened to be greater, okay, than our observed statistic. What is the likelihood that men are taller than women? Well, we believe that that would only happen by chance 50 out of 1,000 times, okay, or 1 out of 20. Does everybody kind of see that? If we get results like this, is there a difference between men and women? Probably yes. Okay? But what are the odds? Well, it happens, we would expect to see this if we had done the experiment 20 times. If there was no difference, we would expect to see this big a difference only 1 out of 20 times. Okay? Any questions about that? Do you see how we can convert these random samples to the idea of a p-value? Okay, yes.
So, what if the observed value would be on the left side of the random?
What if the left side? What if we had something like this? Well, then again, the degree of impressiveness is what's the smaller fraction, right? Now notice that suppose I tell you that I think there's something funny about heights of Martians versus people. What's funny about it? I don't know. Okay. Well, then you're going to be interested in whether it was either unusually big or unusually small. Of course, if you didn't specify your guess in advance, you kind of have to discount the surprise by a factor of 2, right? Does everybody agree that what's the likelihood if I didn't know whether to expect big or small? Okay? My degree of difference is not this size over everything, but this size probably plus this size, okay, over everything. So it should be clear that there's kind of like a divide by 2 kind of thing that's going on, if you don't know what side of the tail it should be on. Okay? But your hypothesis was men are taller than women. If you're telling me men are taller than women, you can test it by what fraction of the random samples would have been, would have had that property. If you're telling me, I think one of them is really quite taller, but I don't know for sure, then you've got a kind of 2-sided test. This is the kind of subtlety that came up. I told you about 2-sided t-tests, for example. This is exactly the subtlety there. Any questions about permutation tests and how they work? Okay? Or why they should work? Basically, again, the idea is going to be, and I'll talk about how we do permutations next class. Okay? But basically, if you take your data, do a lot of permutations, maybe 1,000, maybe 10,000, see where you sit. Okay? Typically, when you're doing the permuting, you typically only permute, you rearrange, let's say, the heights among all the people. You wouldn't change people's heights and weights. So, for example, you wouldn't want to put weights in the height column or height in the weights column. That's weird. You want to make sure you've got a kind of apples to apples test. So typically people permute fields across fields. Okay? And again, when you do this thing, you get a reasonable idea how amazing it is that you're seeing this level of performance. Okay? You guys on homework 3 are going to take the weakest of your variables, try to train a model to predict sales. Okay? Does it do better than chance? How well does that model do? Okay? And that's the kind of thing that you can use a permutation test to tell. Okay? You train it on the real data, you train it on the permuted data. Okay? If your model is doing really well on randomly permuted data, there is a problem. Okay? Any questions? Yes?
So will the distribution which we sample random data will affect the results?
Will the distribution of the sample random data? The answer is, so the question is like, what does it, I think what you're asking, does it matter if the data was a power law let's say, distributed data or normal distributed data? And the answer is a permutation test should be able to kind of ignore that kind of distinction. Recognize that, let's say we were taking a look at, let's say we were looking at, had a power law distribution, okay? And let's say Bill Gates was in the class, and we were looking at wealth of these things. Notice that random samples where Bill Gates was put in either class A or class B is going to greatly, affect the outcome of this thing. If so, then you're going to need to have a big enough difference, observed difference in enough permutations to overcome that thing. So my guess is it will be a lot harder for a power law thing to show up as significant, right? Because you've got these outliers, and these outliers are going to move from one side to another. But that's the way it should be, okay? So I don't think you don't need to precondition this and say, oh my God, every feature's got to be normal, okay? Any question about that? Yes?
I wanted to ask a question that I think students will be asking in the next way, which is when we say we're training on random data, are we permitting the labels, class labels, or the features?
Okay, so you're permuting the class labels or the features, okay? Now, if you're doing if you're building something based on one feature, which is what I think you're doing in the assignment, it probably doesn't really matter, right? Because randomly scrambling the outcome is the same as scrambling the feature, okay? On the other hand, I think typically you scramble the labels. It's cleaner to generally scramble the labels. And if you're trying to build a multivariable model, you would rather scramble the labels, okay, rather than create kind of weird people who are strange mixes of height and weight and stuff like that. So that would be my answer there. Any questions? Okay, we're going to talk next class about how do you generate random permutations and things like that. So think about it, and we'll talk about things then. Okay, thank you. And sorry again for the fire drill.